I'm Aaron Hurst. I'm going to be talking to you today about securing against cross-site request forgery. You may have noticed this isn't the only session about cross-site request forgery. Hopefully some of you had the chance to attend Frank Kim's excellent talk yesterday, where he went over it briefly. And there's also a Birds of the Feather session this evening if you are a night owl. That said, you'll still get something out of this that's unique. In particular, we're going to be talking about ... in a way that you won't regret later. And by that, I mean implementation choices. So we're going to be looking at some high-level implementation options and architectures that secure you against cross-site request forgery and future-proof your application. So I'm Aaron Hurst. The goals I want you to get out of this are, first of all, to understand an attack. I'm going to make no assumptions about your background in cross-site request forgery, so we'll go through this. We're going to talk about protection schemes, sort of the theory behind them, what works, what doesn't work, in particular what doesn't work. We're going to look at implementation for Java web apps. This is not going to be a tutorial, so I'm not going to tell you how to set up each one of these different implementation options, but we are going to look at the pros and cons and how one can still make mistakes with them. And speaking of mistakes, we're also going to look at future-proofing. So even if you implement a cross-site request forgery protection scheme that's perfect today, it may not be tomorrow. So we want to get this right both now and in the future. So why are you listening to me talk about this? I'm from Coverity. We're the leader in development testing. So we have the world's deepest, most precise, and most widely used commercial static analysis tool. So one of our products, Security Advisor, reports OWASP's top 10 vulnerabilities. So that's cross-site scripting, various injection attacks, sensitive data exposure, and of course, cross-site request forgery. So I'm the principal engineer in the Java Web App Security Group. I'm a developer. I am not a security professional in the sense that that's all I do. I don't give speeches for a living. But I do spend a lot of time looking at Java security vulnerabilities. And in particular, I look at Java security vulnerabilities in a wide array of web applications. So I see a good cross-section, and hopefully I've collected some wisdom that I can impart with you about that. So the anatomy of an attack. So cross-site request forgery. I can stop saying the entire long name for it now. I prefer the abbreviation CSRF or CSRF. So when you hear me say CSRF in the future, I just mean cross-site request forgery. The short version is it allows an attacker to trick a client's browser into making an unintentional request to a web server, or at least a web server that's vulnerable. So you can imagine what a vulnerable web server is essentially doing is giving a hacker control of your user's mouse. So you can imagine that they're doing something bad with that. They're probably capable of doing something bad with CSRF. And unfortunately, this is a little bit less well understood than other attacks. One of the other things I do in my role is talk to clients and other organizations about their cross-site request forgery vulnerabilities. And more than once, the response has been, let's get back about that. And it's not something that really inspires confidence in the security field, but it is what it is. And if you're new to this, you're not the only one. So the best way to show an attack is to just walk you through a simple one. So I've decided to bank with my insecure bank. They have a really good CD. It's 1%, so that's good these days. If I log into it with my account, do some banking, what that does is when the request is sent to the browser and my authentication is valid, which it is, I'm going to get a request back from the browser that looks like this, plus some other content. And the request is probably going to include some set cookie directive. And what that set cookie is going to do is set a session ID. So if you're a web app developer, you're very intimately familiar with this concept. But what that session ID is going to do is it's going to serve as credentials. So if I do anything in the future on my insecure bank, if I click on some links, if I go back in my browser, that session ID is going to be sent with every request so that I don't have to type in my password every single time. Generally, users find that pretty frustrating. And that cookie that's set back in this response is going to be put in my browser store, and it's going to be made accessible to other requests to the same domain, to my insecure bank. So in the middle of my banking, let's say I don't sign out and I go browse my other website that I like to go to, Pirate Chat. It's not a MP3 sharing site, but a discussion of all things seafaring. And the pirates, being scallywags that they are, have launched a CSRF attack against me. That's unfortunate. The way that this typically works is somewhere in that web page, the attacker has embedded some HTML that may look something like this. It's an image tag. And instead of pointing to an image that's going to show up and look like a treasure map or whatever you would expect, it's going to point to something at my insecure bank. It's also, you can see that this particular URL includes some additional parameters that look like they're probably going to transfer some money, in this case $1,000 to some account number. And if the attacker correctly reverse engineered my insecure bank's protocol, it's going to do exactly that, if there's no, of course, no CSRF protection. Now me, when I visit this web page, I don't see anything that happened, right? This is not visibly rendered. It's either too small or not a valid image. And the browser is going to automatically load this as soon as I visit the web page. So this happens quickly and instantaneously and not to my knowledge. So this is why it's forgery. So what that looks like is my browser sends an HTTP request to my insecure bank when it tries to acquire this image. So it's going to send it to this transfer address with the parameters that you see in the page. And it's also going to include the cookie. So what that cookie includes is my credentials to do something on my insecure bank. And this comes out of the browser cookie store, and it's totally valid because it's going to the same domain that it was set for. Absolutely. And if there's no other protection, my insecure bank is going to see that as a valid request with valid credentials and do something that I don't want, and probably leave me quite a bit in the red. And because you think you can only do this for GET requests, like I just showed with an image, that's not true. You can also do this with a POST request. So let's imagine the attacker puts some HTML like this in the page. It's a form, a method is POST, points to that transfer page again on the same website. It's got some hidden inputs, right? These are the account number and the amount, same as the last request that I showed. And again, nothing here is rendered. These are all invisible. Now imagine somewhere else, they've also included a script. So this particular script points to the form and automatically submits it. So here now you've got the form that's generating this bad request and the script that's automatically submitting it, and it's having the same net effect as that image that got automatically loaded. So totally unbeknownst to me, I'm again transferring money to the pirates. So how do these things actually get launched in practice? Well, the attack can get launched from many possible places. The site can be one that's just actually administered by the attacker. You can possibly browse to some, let's say, seedy corner of the web, and they might run that website, and you're toast at that point. Websites can also intentionally allow HTML posting. This used to be common on many chat websites. It's less so these days, but it's still out there. So if you're visiting a website that allows such posting, that's another CSRF attack vector. And then any website, of course, that has a cross-site scripting vulnerability is subject to a CSRF attack. So that's actually one of the most common ways to exploit a cross-site scripting vulnerability, is that an attacker will use that to reflect HTML and then attack you via CSRF. So if you're unfamiliar with that, I definitely encourage you to investigate, but I'm sure everyone in this room is well-versed. So the other half of the attack is, well, how do they find the victims, where the victims are both the server and the client? Well, on the server side, they probably just observed an interesting request, something that did something that they wanted to replicate, maybe in some different way, like transfer money, but it can pretty much be anything under the sun. And then they needed to locate some users to perform those actions, users that had credentials that were logged in. And the way that they can feed links to users are actually numerous. So one of the most popular ways is social media. You can just post a link on a Twitter post or put it on Facebook. They can also target it, maybe your website, by knowing what some sites are with related content that might have vulnerabilities and attack those. Or they can just do it scattershot. If 1 million users browse a CSRF attack, most of them don't see anything happening, but one out of those 1 million is a user that's logged into your website, then mission accomplished as far as they're concerned. So, does this actually happen in the wild? The answer is yes. Here's some scary headlines. I Apologize if any of them are your company. You're not alone. But you might ask, okay, sure, this has happened, but what actually is the prevalence of cross-site request forgery vulnerabilities? Well, we're actually coming from a static analysis company that looks at a lot of different code in a unique position to answer that question. So let me just share a little bit with you what we found. So as part of constantly improving and evaluating our tools, we analyzed a whole set of Java web applications, a couple dozen. And I've collected some statistics here about the vulnerabilities that we found. Now, obviously, this is biased to what the tool can find, and you can take it with a grain of salt if you absolutely want, but it's at least some quantitative measurement. So here are just 5 vulnerabilities. On the right side, we see SQL injection. That's where a SQL query is some malicious code is injected into it. Java web app developers have known about this for years and actually have done a pretty good job at remediating against it, so there's not as many of those. Path manipulation is where some unwanted directory traversal is injected. Risky cryptography is pretty self-explanatory. Other than that, the next biggest is cross-site scripting, and dominating that by over a 2-to-1 factor is cross-site request forgery. So this is open source web applications, and there are some bright spots in that field. Some of them are doing it right, but it's a fair characterization to say that they're a little slower in the uptake of security fixes. So you might ask, well, what about enterprise applications? And at least there's a measurement for open source web applications. There's about 120 CSRF vulnerabilities per million lines of code. Interesting to note. For enterprise web applications, we see about the same pattern. It differs a little bit. These 2 example companies are doing some things right. One of them has no SQL injections. Both of them have no risky cryptography that we could detect. But cross-site request forgery is still the #1 average issue between them. So it's a problem in both the open source world and for enterprise applications. So you've been attacked. That's unfortunate. What are you going to do? Well, one of the problems with CSRF is that it's difficult to distinguish between real and forged requests. From your point of view, as a server administrator, both of these requests come from the client's browser, both of them come from the same IP address, and both of them come with the client's credentials, so like their session identifier. If you look in your Tomcat log, both of them are going to look the same. So if you want to imagine some sort of programmatic way to unwind an attack, like go back to some previous safe data and then replay it, it's very difficult to do because the attacks are indistinguishable from the actual requests that the users make. So it's really tough. There's not much you can actually do short of calling up your users and saying, did you actually intend to make that request? But that probably gets pretty tiresome for them. And I don't know if it makes me a bad person, but I'm still waiting for my stockbroker to call me and ask if that time I sold Apple in 2000 was a CSRF attack, but hasn't happened yet. So the only answer I have for what to do if you're attacked is to give some tough love and say that you need to protect beforehand. So when we want to talk about protection, I want to just start off by saying there are a lot of things out there that don't work. Some people think that they do. One of the very first suggestions to fix CSRF was to use only post requests. This was from the early days when the vulnerability first appeared, and was based on the fact that people only knew about the image attacks, so they were only seeing the get CSRF attacks. Of course, as I've just shown you, you can do the same thing with a post request, so that's not valid anymore. HTTPS, you should use it. It encrypts your link, but it has no protection against cross-site request forgery. I've seen on some bulletin boards a lot of interesting suggestions about doing things to the session identifier to help with CSRF. Some ideas were multiple session identifiers for the same session. You can change the length or randomness. One suggestion is to shorten the expiration of the session identifier, and this, of course, does shorten the attack window that someone can hit you with a CSRF attack. But if you're happy with a shorter attack window but still vulnerable application, that's the way to go. If not, you need to do something else. And one of the more interesting suggestions that I've heard lately is the use of "Are you sure" dialogues. So the idea is to pop up some dialogue and ask the user if the action's really intentional. And that's a really good way from preventing unintentional things happening in your legitimate web code, it has no use whatsoever for the attacker's attack. So they're just circumventing this and doing whatever they wanted to do anyway. So there are some things that do work, fortunately. We're not all at the mercy of rogue pirates. Refer validation is one of the things that does work. Many web browsers include a refer header that describes the origin of the request, so what page you browsed from. The problem with this is it's not always present. Some browsers can remove it. There's actually some network hardware that can remove it, and usually this is done for privacy reasons because it's telling you where you came from. And not everyone wants you to know that. It's also not present for certain transitions in between HTTPS and HTTP. So what do you do for these cases? Well, you have two choices essentially. One choice is you can be lenient about this and allow these requests to proceed. The problem is that that's going to be insecure, so you're still vulnerable there. Or you can be strict about it and make your website inaccessible to those users that have their refer header stripped. So that's a tough choice. Another option is custom headers. So instead of using refer, you can actually add a header of your own. So you can do this using JavaScript. There's the XML HTTP request function. One of the things it can do is allow you to add your own header. The problem is that you can only use the JavaScript XML HTTP request to send your post requests. This doesn't work with HTML forms. So if you have any forms or any sort of legacy HTML of that sort, this is not a viable solution for you. The reason that this does work is that all modern browsers respect this same origin policy. And what the same origin policy restricts attackers from doing is to add a custom header to a request that goes to a different domain, or different origin. So a different origin is defined as some website with a different scheme, hostname, or port. So the browser prevents CSRF attacks through that restriction. So the most general solution, and the one that we see most often in code, is the use of secret tokens. So the way that secret tokens work is that the server generates some shared secret between you and the legitimate client. This is included as a hidden form parameter. So here we've got some HTML form that does something, the canonical trans, for example. And it's got a hidden input that we inserted. I called it anti-CSRF, but you could call it anything you want. And it's got this shared secret token that the server has generated and stored and remembered. So then when the user goes and submits that form, the server checks that the token value that's submitted is the one that it had previously generated and stored. If it's valid, then the request action is completed. If it's not valid, then you know you have a forgery on your hands. So the way that this is secure is that it also relies on the browser's same origin policy. The DOM is inaccessible to pages from another site. So that hidden field in the form, you can't access if you're an attacker with HTML on a different page. The token has to be, of course, unguessable. Most people just use cryptographically secure random values, like similar to a session ID, but not a session ID. If you're using your session ID as your CSRF token, then something's bad. You're bound to get hosed sooner or later. The token also needs to be temporary. Most implementations use a token lifetime of about a session, so between the user's login and logout. You can actually do something shorter if you're really, really concerned about CSRF. The problem is that users may find this annoying because if the token expires and they hit the back button on the browser, then the request gets rejected for being invalid, and that's not ideal. So just to illustrate, to make clear how these secret tokens foil attackers. So let's say my insecure bank hired a really sharp security guy, and he went to fix all their problems. He might consider adding, again, this anti-CSRF token to their page, the transfer money page. And when the user goes to post this particular request, they get the cookie with the session ID, that's their credentials, the account, the amount, and it also includes the CSRF token. The corresponding hacker's request doesn't have access to that value, so they can leave it off. And then the server will just reject that request. So that insulates my insecure bank from these forged requests. So next I want to move on to some implementation choices. So I'm going to focus mostly on the use of secret tokens. I think the custom headers and the refer validation are pretty self-explanatory. If they work for you, that's all the better. But with secret tokens, we need to do two things. We need to answer the question of what do we need to protect, first of all, and then make some choices about how to protect it. So as far as what to protect, basically anything that modifies the web app state is something that you should at least consider protecting. Database updates, changing anything on the file system, things that are long-lived attributes, so like session scope or application scope attributes are things that you might want to consider protecting. Interestingly, login pages are something that are often forgotten. So login pages don't typically have a session identifier, but because they're updating the web application state, they're in fact setting the session identifier, it is possible to conduct a CSRF attack against the login page. So I'm not going to go into this particular attack in any more detail, but I absolutely encourage you to investigate it if you're not familiar. And one of the things that's challenging for enterprise applications are if you have backend services that you're communicating with from your front-end web servlet. These are things that may modify their own state, and they need to be protected just as much as if your web application were changing the database. But you can't go and protect everything in the web application. Life would be much easier if you could. You could just deploy your protection and forget about it. But you need to implement some holes in it, because there are certain things that can't be protected, or at least are functionally incorrect to protect. Some examples of these are landing pages. So if someone's intentionally browsing to your website from another domain, you don't want to protect against requests from another domain. Things that are stateless or unauthenticated, these are not something you care if someone's forging, right? If it's an unauthenticated form submission, like maybe an account sign-up or something, the attacker could very well just do that on their own. They don't need to forge it from your client's browser. And in general, anything that's bookmarkable. So these are links that you want to be long-lived, and the CSRF token is not long-lived, so need to be holes. So when looking at the code that we've seen through our static analysis investigations, we can say that maybe most checks fall into one of three broad categories. So there are probably other ways to do this, but almost everything is one of these three ways. First one being manual checks. So when I say manual check, I mean some programmatic way to check at each entry point whether the CSRF token is valid. So here we've got a servlet. It's a do post handler, so it's handling post requests. And you can actually just insert a function call that's checking for the parameter that you expect, whether that's a CSRF token that you've previously generated. If it's not, then throw an exception, don't go any further, and you've protected yourself right there. Manual checks are nice. Your servlet container is dispatching to any one of your request handlers, and you can introduce this sentry at whichever ones are needed. So here I have a little sentry icon, right? It's a 2 out of 3. This gives you a really nice tight coupling of the functionality and the security. So you have a really fine-grained control of the protection. So this is nice because you need to decide on a request-by-request basis whether it needs to be protected or not. The downside to that is that you need to decide for every request whether it needs to be protected or not. So developers need to think about this. It's no longer set it and forget it. You have to think about CSRF every time you write a new entry point to your web app. Not ideal. And the more opportunities for you to make mistakes, the more opportunities someone's going to get into your application. So pros and cons. Servlet filters are another way to implement CSRF protection. This is actually the one I think is most common. You can actually do it using a servlet filter, or I'm going to lump some other things into this category, like I know Spring has some mechanisms to do something similar. And the servlet filter is just a single monolithic check for your entire web application. So it's checking the request for all of your specific individual request handlers. And the bad side of this is that it's a loose coupling of functionality and security. So what you need to do, and what you need to get right, is correct behavior in two places. So your requests are either updating the state of the application or not, and your servlet filter is either protecting the request or you're not. And if those two things aren't synchronized, then you've got problems. You've probably got a vulnerability. Last but not least, there are some anti-CSRF libraries out there. So Frank mentioned yesterday OWASP CSRF Guard. Probably the heavyweight in the room is Spring Security. They now have a CSRF solution since version 3.2. And Apache has something equivalent. And these are really nice. They give you code that does the token generation and management. You're going to avoid errors in that. They also do a lot of the legwork for you. So they have some ways to modify all your views so that the forms will submit the CSRF tokens. And that's great. You don't have to change all those. That's a lot of implementation effort. But they don't solve all the problems. In particular, they don't tell you how to protect something. Or sorry, they don't tell you what to protect. They all make some simple assumptions about what parts of your application need to be protected or not, with some limited configuration. So if your application is more complicated, or your security obligations differ in some way from the configuration dimensions, then you're a little out of luck in these cases. And they also have known security weaknesses. So one of the examples is that they expose tokens. So the token is added to forms, and the token is added to forms to your website, but also to forms that are submitted to other websites. So in the off chance that your form's being submitted somewhere that you don't want the person to know your anti-CSRF token, then that's possibly a security vulnerability. So there are some challenges to using any one of these CSRF protection strategies. So I'm going to, in this section, focus a little more on some code examples. So we've collected some from open source. Hopefully this illustrates things not to do. So the challenges are essentially, how do you implement these exceptions? So you've got to specify or define them in some way. And you've got to decide and evaluate whether they're correct. Doing this requires both some security expertise, so you need to be able to evaluate the security consequences of it, but you also need some knowledge about the functionality of your application, so you need some development expertise as well. And finding someone that can wear both of these hats is often very challenging. These organizational roles might not be found in the same person. They might not be found in the same part of the organization, or even the same half of the world. And also, retrofitting an existing system is really challenging. So it's nice if you can generate a new architecture so that you're customized around one of these CSRF protection schemes. But if you've already got a web application that's in the field, you can't change the architecture of the request to match what it expects. So there's some additional challenges if you have to backport CSRF protection onto something that is already a functioning web app. So the single best thing that we've seen to minimize your risk of CSRF vulnerabilities is to use the correct HTTP verbs. So if your application is RESTful, or you subscribe to that philosophy, this is going to make your life much easier in terms of CSRF protection. The reason is that these HTTP verbs, so get, post, put, delete, they give a language that's meaningful to developers. Most developers know when you should use each one of them. And they also simultaneously capture the security obligation. So you've got a developer, he sees a GET request, he knows that this is something that you use for requests without side effects, something that's idempotent. Post, put, or delete, right? These are things that you use for requests that have side effects or change your web application in some way. And your security auditor, when he sees these two things, he sees a GET request and he knows that it's something that doesn't need CSRF protection because it has no side effects. And post, put, and delete, these are the vulnerable entry points that need to be protected. Our security auditor has a tie, I just noticed. I don't know about your organization, but I think our security guys are the least likely to wear ties in the company. But I'll change that one next time. So that's great if you do that. The problem is that it's easy and tempting to not get the HTTP verbs right. Everyone's got that one case where you're RESTful in the rest of the application, but you just want to use a GET request for that one state change. It's easy and tempting. So here's a piece of code from a Java open source web application. It's a Spring MVC 3.0 controller, some cart. So you can even read the comment what it's doing. It's adding an item to the shopping cart. And you can see that it's an entry point because it's got the request mapping annotation. And you can see also that the request method that it's handling are get and post. So clearly, if the rest of the application is RESTful and this is adding something to a shopping cart, you don't want to be using a GET request to do this. So the reason that this is a security problem is that if someone comes along and expects that only post requests need to be protected, this one thing is going to be a glaring hole. It's going to service GET requests that are state change, and that's not going to be protected by this post-protecting only CSRF scheme. So, and that's in fact many of the schemes that many of the anti-CSRF libraries use. So this is problematic. So are there any Spring developers in the audience? So, okay. So anyone know what happens if you leave off the specification of the request method? Right, it serves all of them. So that's even easier to mess up, in my opinion, than to get it wrong, is to just leave it off. So this is particularly problematic, again, because it's functionally correct. It's going to handle the request method that you expect, but it's also going to handle the ones that you didn't protect against CSRF. So that's a giant gaping security hole. So I've talked about using HTTP verbs. Not everyone can do that. Like I mentioned, if you're a legacy application and you've already got some transaction architecture, you may have to resort to something else. Fortunately, that something else isn't pretty. So here is a example web XML file from a Java open source web application. So what they're doing is they have some filter class that's protecting them against CSRF, and they have exceptions because they need holes, like every web application. Unfortunately, the way that they're specifying them is very difficult to understand. So it's a comma delimited list of both a combination of web XML styled URL patterns and some regular expressions. So if you are coming to look at this for the first time, you're a new developer or security auditor, how in the world are you supposed to tell what's protected? So there's also even something fishier with this that an early audience member of my slide presentation noticed. They suspected it was a copy-paste error. Anyone see what it is? So it's the last three lines, the last three regular expression lines, don't have a comma after them, whereas the rest of them do. So what does that mean? Who even knows? This is some custom code. If they get it wrong, that's their problem. So here's another example of if you try to do this on your own for a complex application. This is a way that a particular enterprise web application specified the exceptions in their servlet filter. So this is essentially the logic diagram for the servlet filter that they implemented. And this didn't come from a nice piece of documentation or a specification. I had to extract this through some very deep code archaeology. So on the right side, you can see it's just like a flow diagram of the various things they're checking to decide whether they want to require a CSRF token or allow the check to go through. And the places that the data are coming from that allow them to determine whether that should be accepted or rejected are a set of hard-coded literals in the code somewhere, not in the servlet filter, multiple property files, and some parsed XML trees. So if you're, again, an auditor or a developer and you want to add an exception or evaluate whether it's correct, what in the world do you do here? It's at least not an ideal situation. The one thing that you can do is at least to verify that you've got it correct. So if you take the simple route and use HTTP verbs to define what your protection obligations are, you can at least enforce or verify that they're used properly. So that's pretty easy to do. And if you need to make any exceptions, maybe because you're not using HTTP verbs to decide your protection obligations, you need to carefully evaluate them, maybe with the security auditor sitting behind you, or at least someone that's very knowledgeable about the web application. So you need to ask yourself whether the request handlers are changing the server state. But wait, how do you even tell that? So I've got another example here. This one's from an open source Java web application. It's a request handler. So if I want to decide whether this changes the state or not, I look at this code, and I'm going to spoil it and tell you that there is a side effect in this method. But can you even spot where? Any guesses? Yeah. What was that? That's actually a very good guess. Got it right. To me, that's not obvious because it's getting the root content VO, so this is just a view object, but it actually writes to the database exactly like you said if it didn't exist. So you'd make a very good security auditor. But I don't expect that a security auditor that I hired would look at this code. And let's be honest, they would probably look at this code for about as long as we just did right here, because there's many other entry points to consider. The chances that they find this based on this innocuously named function are, I think, close to zero. So what can you do? Is there anything we could do to make our lives easier? We've got to make sure that these things are implemented correctly. So one approach that I know a little bit about is static analysis. So this is at least one tool in the toolbox that you can use to make sure that your cross-site request forgery protection is correct. The way that the static analysis approach works is that we use a tool to automatically identify the methods that update the state of the application. So again, these are the things that have database rights, file system rights, etc. We can also use the tool to compute the coverage patterns of whatever CSRF protection you've implemented, if you've even implemented any. And this can include things like looking at the URIs that filters are mapped to and whether they intersect the URIs where your web request handlers live. It can be looking at the manual protection at every web entry point, whether it's present or absent. And for these libraries, it involves digesting some of the configuration to see how you've set it up and what URLs and what request methods are covered. So if you can automatically compute the coverage patterns, where the vulnerabilities live is in the intersection of these two. If you update the state and you're not protecting it in any way, it's at least something that a human needs to look at. So just to give you a quick look at what some of these look like, I'll give you a walkthrough. This is our web application. So you can run static analysis on your source code. You run it once, get a set of results. And in our workflow, you commit it to this web tool called Connect. It gives you a list of all your issues. We're looking at some source code. Here it's annotated, so that all these red and orange boxes you see here describing the things that are happening in it that the tool is derived. And then on the right side, we've got a navigation pane with the list of events. The rest of this involves ways to manage the defects and track them and triage them and make sure that you're following up on fixing them. I'm going to ignore that for now since I want to talk about CSRF. So let's dive into a piece of code. So here's yet another CSRF defect. So let's tear this one apart, see how they're doing this. So what the tool is telling us first is that it's identified a request handler. So you can again see that there's a Spring request mapping annotation. If I were to look at this, I would see that, hey, it's a save review method. It's probably doing something to update the state of the web application. In this case, I think it's saving some sort of product review. The tool, of course, doesn't know that based on the name review item, so it has to accumulate some evidence in another way. But it can still identify that there is a state update. So here it's called out this call to rating service.review item as something that's updating the database. So the reason it knows that is that in this particular case, our tool is interprocedural, so it can dive into callees. So if we ourselves dive into the callee, you can just click on it in the web interface. It will show you what it thinks about what's happening in that. So here, if we look in the review item, it's in the rating service impl.java, so it's in the not in the interface, but the implementation. I've allotted some of the lines of code, but here it's calling out another call in this. So a call to the rating summary, DAO.save rating summary. Again, any human looking at this could at least tell that this is going to update something in the DAO layer. But the tool also gives you the full chain of justification of why it thinks that this updates the database. And at the very bottom of that chain of justification, here's this call to em.merge. So this is, of course, a call to Java Persistence Entity Manager, which is a ORM write database update. So the other half of what the tool is telling you is not just why it thinks you need protection on this particular entry point, but why it thinks it's not there already. So in this case, it's noted that there are manual checks elsewhere in the code. And in fact, it's going to show you examples of positive checks as evidence that the entry point we just looked at was missing one. So here, somewhere totally unrelated in this particular web application, you can see it's a different controller, the upload, add, or update controller. It's highlighting a CSRF check. So this is pretty obvious from the comments. It's a check for X6 same thing, just different acronym, XSRF. And there's a call here to this exploit protection service.compare token. So it's exactly just checking the service object has generated this token previously. It's just checking that it's a valid one. So we actually find that this particular half of showing security defects is the most important half. So this is the remediation advice. So if you actually have to fix this, it's not enough to just tell a developer who may not be familiar with CSRF, maybe new, may not know how you do it in your web application. It's not enough to just tell them that they're vulnerable. It's very valuable to also show them how to remediate it. And this holds true for all sorts of security vulnerabilities, since that expertise isn't present always in everyone in your organization. So here's just a quick quiz. I want to see if you're paying attention, because in this entry point, they violated one of my rules. Anyone see what it is? I know the code's small, I apologize.
The request method, yeah.
Exactly. So this is not using the HTTP verbs correctly. Never a good idea. In this case, they implemented their CSRF protection using manual checks, so it's not going to actually necessitate that there's a vulnerability because of that. But if they were to switch over to something like using OAuth CSRF guard, which protects post requests by default, then this would be left out in the open. So, good eye. Okay, just wanted to wrap up with some conclusions, at least about what we've seen today. Don't let anyone tell you otherwise. Sound cross-site request forgery protection is difficult to get right. And usually the way to get it right is to not build additional complexity into it. And I realize it's very, very tempting to build additional complexity into already complicated enterprise web applications. But the simpler you can keep it, the more likely you are to get it right. And particularly, the more likely you are to get it right in the future. HTTP verbs, use them. They're a great language, they're already there, they're well specified, and they also capture the security obligations for cross-site request forgery. This is probably a piece of advice that applies to any developer anywhere, not specific to cross-site request forgery. But be clear about what your method is doing. Especially in the case where you have a human auditor looking at your code or maybe evaluating the result of the tool. You need to see what the method's doing and be able to quickly make a judgment about the side effects. So you don't know what to protect if it's not obvious to you. And, well, you probably could guess this already, but having some verification is important. And probably, actually, from a security point of view, having multiple methods of verification is important. Having human auditors look at code, employing any tools that you can use, static analysis. The more you can unleash on your application to find these defects and vulnerabilities, the more likely are you to avoid the pain of CSRF. So I'm going to open up a few minutes early here for a question and answer. If you have any curiosity about the technology, that's the website. We've also got this free Java software quality evaluation going on. And when I say quality, that doesn't unfortunately include the cross-site request forgery checker, which is looking for a security vulnerability. But I'm sure it will still uncover lots of interesting quality violations that are similar to this one in your application. And with that, any questions?
I have one remark to that. For a GET request, I think in some cases you still need CSRF security.
Yes. So the comment was that for GET requests that you still need some protection in many cases. And that's absolutely true. If you don't partition your verbs correctly, so if you're still doing some sort of state-changing transition with a GET request, which is totally fine to do.
Even if there's no state change. I think its concern is that the attacker can still do a GET request. But the reason it's not a problem is the GET request will just be served up to the authorized user's browser, and because of the same policy, that information can never be exposed to the attacker. So if you have a cross-site scripting and some Ajax, you can still send the result not across to the original.
Yeah. So keep in mind that from the attacker's point of view, when they unleash one of these pieces of HTML on like some chat site or in some vulnerable website, and you run it, they don't actually see the result. So it's not necessarily a direct pipe of information back to them. But if it has some side effect that in some way becomes visible to them or they're able to use, like a money transfer to their bank account, but there are many other similar things that are a little less crazy that CSRF attackers can do. So they're really gaining the value through that side effect, not necessarily through a flow of information. But you're right. I mean, there are many other web application vulnerabilities that are caused by sensitive data leaks. But yeah, I don't think that this particular protection scheme will protect against those.
We have an environment where we have stateless servers with no session affinity in a clustered environment. So 2 requests, one may go to server A, one may go to server B, and there's no session. Is there a better solution than generating a value and then signing it with a secret key and checking that the value was in fact signed with a secret key? It seems very complicated.
That's absolutely true. It is pretty complicated. If you can use one of the simpler methods like custom headers or refer validation. Sorry?
That's to originally authenticate, but then to stop CSRF. I'm not sure how it all helps.
Yeah, it's sort of orthogonal issue to authentication, because you can still get authentication wrong, but in cases where the user is authenticated correctly, what the CSRF attack is, it's using that authentication to do something even additional and unwanted. So yeah, I unfortunately don't have an easy answer for you, but that's the state of things at this point. Question?
Your security advisor, is it part of your co-advisor? And the product, is it a separate product or is it part of another package?
They are separate products. So we have a question was about the product hierarchy at Coverity. So there's a product called Quality Advisor that finds these sort of concurrency, resource leak, all sorts of software quality defects, and that is sold separately from the Security Advisor, which is targeted to Java web applications. A question?
You mentioned the OWASP CSRF card, and I think you quickly mentioned that the token could be visible when you change domains, I think you said. We're using JavaScript injection, we're using the first session token. Can you tell me a little bit more about how that's insecure, or maybe where it could be?
It's not necessarily insecure. So if you don't trust where you're submitting your forms to, so if they're going to some other domain, the problem is that these tokens get added to everything unless you do something to remediate that. And if an unsecured person in another domain is receiving your form, it's going to have that extra token in it that gives information that they could then use to launch a CSRF attack through some other vector. You probably don't want the token in anyone else's hands if you can avoid it. Again, it requires a specific security evaluation of that particular system and what your trust levels are to the various entities, but it is a potential vulnerability for some people. Got a question in the front?
So the only thing I need to worry about if I use custom headers is that the token is unpredictable, and that's all I need to ensure, and everything else is okay.
So for custom headers, you don't actually even need to use a token. The reason is that you can only add a custom header to a request that's originating from your domain. So that header won't even be present. There's no way to add it, right? Because of the browser's same origin policy. If that request is coming from HTML on pirate chat or some bad link, right? That can't add that header and send it to your domain. So you're safe just by the presence of that header. Don't need to worry about the token generation in that case. So question over here?
You said earlier about expiring, other than just a good idea in case it ever does get into someone else's hands. Is there any reason beyond that why you would want to expire?
The question was, what's the justification for expiring the CSRF token? And yes, it's absolutely to prevent that from leaking somewhere. You absolutely should make it on a per user basis, right? If you're using the same CSRF token for the whole application, then the attacker can create an account and see that and forge other people's requests. But how often you should change it is just a matter of your comfort level with that persisting. I mean, users can still leak these things if you kept it around forever. If someone would copy and paste, right, maybe a page source to show an example on a web developer's forum, it might accidentally include the CSRF token, right? And in cases like that, you want to avoid, but yeah, they're pretty rare.
Might of course use your phone and your phones. If suddenly all the access into your bank account is on forever.
That's an excellent point. The point was that if you lose your phone, then you've lost your CSRF token, and now you're vulnerable to attack if that is persistent. So there's a question in the back against the pillar.
I may have missed that last one, but so in your example, you showed that that token was part of the form post.
Mm-hmm.
Is it any less secure or more secure if you were to put that in, say, a HTTP only secure session cookie scope?
Yes, that will not provide you protection against CSRF. The reason is,
But in your example, you had to modify your form to have that token in the form. So if you were to serve it down in a cookie,
yeah.
you still need to do the check and serve, right? You're any less secure using a cookie as a
Well, the problem is that serving down in the cookie doesn't have the same origin restriction. So that cookie gets sent with a request to your website, even if it comes from somewhere else. So you get hosed that way. Question back there in the black?
Yeah, if you do not have HTTPS protection, you lose the token anyway.
That's true.
So you won't need to do a request tokens, would you?
Yeah,
Something like that.
the point was that if you don't use HTTPS, then the request traffic is subject to snooping, and you could lose the token that way. And the point's absolutely correct. I guess the best you can do in that point, if you're assuming that attacker is snooping everything and you aren't able or aren't willing to use HTTPS, well, you've got a hole there. I guess the best thing you can do is to change the token as often as possible. Yeah, absolutely right. Question?
Does it matter if you put the token in the header or the body or the query?
So the question was, does it matter where you put the token? Well, it needs to be in the form, if at least if you're using traditional HTML forms. So wherever the form is in the body is where it needs to be. If you're doing something more sophisticated, like using JavaScript to send these XML HTTP requests, you can put it in the JavaScript in the header. That's fine. The reason is that the header is, like the rest of the body, is also protected by the same origin policy. So you're safe there. Got a question in the front?
So I'm not so much into the UI part, but one question, like you're using JavaScript to generate this anti sort of token. What happens if you close the page and start another session with the browser? Then how do you persist that token?
So the question is, how do you persist and manage, I think, in general, what general management strategies for the tokens? So usually what happens is, the way that it's most commonly implemented is on the server. When you initiate a session, the same time you generate the session ID, you just generate a new CSRF token that's valid through that session. So if there was an old one and you generated a new session ID, you might as well just generate a new CSRF token. As long as you know what the valid token should be for a request. So later, if they browse somewhere and come back or don't log out, that token will still be stored on the server somewhere that it can be checked against. Good question.
You mentioned about login pages also need protection. So I know there's a common thing, once you've achieved your login, you normally roll your session as well. So I guess you also roll your CSRF token at that point, once your login has succeeded.
Yeah, that's a common way to do it. I mean, like I said before, you can have it even shorter lived than that. That any time you generate a view, you can generate a new token that corresponds to that view.
But then your navigation might be, if you go back.
Yeah, that's exactly the problem. So it's just convention that the common point to do it is at login. Like we were talking about earlier, you could even keep it for longer than a login. It's probably not a good idea, and I definitely don't recommend that. But as far as if that token is kept secure, that does work too. So generated to login is the best way to go. So a question in the back?
You briefly mentioned something in particular about login page. You said there is some complicated vulnerability about that that's too much going to. Can you point me to what you're talking about?
Yeah, I suggest Googling it. You can find, I think there's an academic paper about it that guides you through it. Generally, the idea is that the attacker can forge a page and have you log in as them. So then essentially what gets stored is a session ID that corresponds to the attacker's account. And then any actions you perform will possibly leak information to them or do something with their credentials on the server. So to protect against that case, it's obviously not possible to use this CSRF token for that case, but there are a few other ways, including the ones mentioned with headers. The way that is also always safe against CSRF is the use of a CAPTCHA. So if you have a really secure account, or if you're generating an account, logging in a particular secure way, CAPTCHAs are safe.
I think the server-generated token, that means if I were an hacker, I would be able to detect that you're asking for extra token. Next time, I would know that I would grab from the user's browser from that domain anyway, and I can still attack you.
So the question was if the hacker becomes aware that there's a token, how they might try to grab it.
Yeah.
So there's two ways you can imagine that they might grab it. So if they have access to your wire and they can see what the server is actually sending, right, then that's you're vulnerable.
I can just get it from the same user browser. It's just another cookie.
Well, it's not a cookie. It's something that's in the HTML of the page. So it's actually in the form HTML. Yeah. So, right, obviously if the hacker had complete control of they could define the browser code, that is information that's in the browser somewhere. But all the modern browsers partition it so that that's kept in a sandbox so they can't actually see.
I'm asking too much question, but
No, that's
if I close a browser, that means you lose the HTML page. That means you would lose the server-side token next time I open the page, right? You have to relog in.
You get that token sent again when the user gets to the page because it's in the form.
If the user gets the page, the token is gone because you're not going to cache that.
No, it's in the form, so the form is sent with that token.
I close the browser.
When you open again the browser,
You're talking about
you ask another type the form and you get a new form with a new token. So,
okay.
Yeah, there's some trick to how you manage the tokens on the server, and that requires some sort of caching mechanism. You got to keep it for a certain length of time. And this is actually one of the reasons why using one of the anti-CSRF libraries is great. They all implement that and they do it well. So they keep this cache and you can set the expiries and there's nice policies about that. So as far as implementing that, I highly recommend looking at those. Any other questions? All right, thanks for staying late. I really appreciate it.